In 2019, the European Union embarked on a journey toward a green and more sustainable future through the Green Deal, with the ambition to reach climate neutrality by 2050. To fulfill this target, the EU should deploy massive renewable technologies capacities to decarbonize its energy mix, electrify its mobility sector, and wherever possible, its most carbon-intensive industries, by also exploiting the potential of digital technologies to maximize energy efficiency. The EU is not the only region that is trying to lessen its dependence on fossil fuels and committed to limit the rise of global average temperatures below 1.5 degrees Celsius by the end of this century. According to the latest projection of the International Energy Agency, renewable power generation capacity rose from 4.3 terawatt-hour today to nearly 10 terawatt-hour in 2030 in the stated policy scenario. This rapid increase is mainly driven by China. It accounted for 60% of the new renewable energy capacity added worldwide last year, with solar photovoltaic generation being on course to exceed, by the end of this decade, the total electricity demand of the United States today. However, this massive transformation of energy systems to mitigate the worst effects of climate change globally is not happening in a stable geopolitical context. Since the launch of the EU Green Deal, the world has rapidly changed. The COVID pandemic and the technological competition between the United States and China on semiconductors and AI-related platforms had put pressure on the stability and security of global value chains, while the Russian invasion of Ukraine induced an energy crisis whose long-term consequences are still felt by European consumers and companies. Notwithstanding these issues, the EU remains committed to reaching its Green Deal and digital targets, but it still faces challenges in a new global scenario where economic interdependence is becoming more a tool for coercion rather than for cooperation among states. This scenario is particularly relevant for critical raw materials, the building blocks of renewable and digital technologies. Which minerals and materials are critical and why are so important for the EU? Critical minerals are commonly referred to as those that show high economic importance and concurrently exhibit high supply risks. They are essential for manufacturing electric batteries and vehicles, such as lithium, cobalt, nickel, and manganese, or rare elements, which are almost irreplaceable for permanent magnets used in electric motors, wind turbine generators, and some military applications. Others are mined in very tiny amounts, such as gallium and germanium, but are essential for semiconductors manufacturing, both for digital application, but also for photovoltaic cells, such as silicon metals. If their economic importance as added value for these industries is increasing, their availability on international markets cannot be taken for granted for several reasons. The first one is that global demand is skyrocketing in different scenarios. According to the International Energy Agency, clean energy technology will boost demand by a factor of 2 and 3 by 2030 and by a factor of 4 to 6 by 2030. This rapid increase will put pressure on supply, which at current level remains highly concentrated in few countries, especially China, which is one of the major producer and refiner of some of these minerals and metals, and also a relevant state-backed investor in overseas deposits located in South America, Africa, and Southeast Asia. Some of them are also active members of the Belt and Road Initiative. Furthermore, developing mineral deposits is a risky endeavor, having high capital costs and environmental and social impacts that must be carefully managed, while refining minerals into usable metals is an energy and know-how intensive process. These factors have gradually impacted the relevance of Western countries, with the notable exception of Canada and Australia, in these industries. For instance, the EU share of the global production of most critical raw materials is lower than 7%. The new global context thus requires actions and policies to secure stable supply. Without lithium, we cannot store renewable energy or run an electric car. Without silicon metal, we can build sophisticated microchips to perform AI tasks. Without titanium, we can conceive spacecraft and military applications. As past transition have shown, those who can master and control this metals supply chain have an indisputable power to lead innovation and high-tech manufacturing, thus projecting economic power. China has long recognized this and gained, with long-term industrial and trade policies, leadership in manufacturing lithium-ion batteries, solar photovoltaics, wind turbines, power electronics, and others. With a massive industrial capacity and mature market, China is thus a dual provider of materials and high-tech components. This dependence is particularly evident for the EU for natural graphite used in batteries, but also for gallium germanium, on which Beijing also recently imposed export restrictions. The EU is also dependent on Chile for battery-grade lithium, on the Democratic Republic of Congo for cobalt, and Brazil for niobium, a rare metal used in high-performance alloys. While import dependence is not per se an indicator of supply risk, it is nonetheless a significant factor. Faced with these short and long-term vulnerabilities, further highlighted in its latest study published in 2023 that updated the list of critical raw materials to 34 items, 17 of which are deemed strategic for their use in multiple sectors, the European Commission has decided to launch a series of initiatives to strengthen EU strategic autonomy in the clean tech race. Approved in March of the last year, the European Critical Raw Materials Act proposed a series of non-binding targets to be achieved by 2030, including 10% of EU critical minerals needs from domestic mines, 40% of refining from European plants, 25% for recycling, and no more than 65% of imports from a single supplier. The speed of adoption of the proposed regulation by the EU institutions has confirmed the urgency of action on this front, but some loopholes remain and risk making these targets, if not unattainable, at least ineffective. First, no public funding is provided to support these activities, but only a more accelerated permitting regime, especially for projects deemed strategic to European interests. Unlike the American Inflation Reduction Act, there are also no tax credits to incentivize local industries to prefer domestic supplies. On the diplomacy side, although the Commission has already signed trade partnerships with research-rich countries, including Canada, Namibia, Kazakhstan, Argentina, Chile, Zambia, and Congo, on behalf of the EU member countries, it remains to be seen how and how much public-private funding will be dedicated. In addition, domestic political fragmentation over the desirability of the green transition is making very complex to implement the EU industrial strategy. As also recalled by the Net Zero Industry Act, with the goal of producing at least 40% of low-carbon technologies to be installed on European soil by 2030, the prospect of uncertain demand coupled with high energy costs makes needed investments in upstream stages of the supply chain, from mining to refining, difficult to materialize. According to some estimates, domestic supplies of critical minerals could meet the EU demand for some materials by 2030, but they require some certain market and political conditions, such as more stable prices and demand visibility. In the long term, the strategic autonomy for the EU in these sectors will also hinge on the ability to innovate and leapfrog existing technologies. For example, the development of sodium-ion batteries could reduce the dependence on lithium and on Chinese suppliers for battery materials. But the recent financial difficulties of the EU-backed startup and battery champion Northvolt are twofold insights. First, the pressure of Chinese overcapacity on the commercial viability of the EU-led gigafactories, and secondly, the relative immature markets for EVs in Europe. The EU must face an inevitable trilemma: pursuing Green Deal objectives while safeguarding its economic competitiveness and reducing material criticality. While there is no certainty whether the EU could address contemporarily all these issues, solving them will require a systemic approach that involves all stakeholders, because powering the green and digital transitions requires resources, but resourcing materials also needs more powerful initiatives.